Hi everyone. So today it's a great pleasure to have Andrea Angiuli, who is currently at Amazon after graduating from the University of California at Santa Barbara. And so Andrea is going to talk about reinforcement learning for meaningful games and mutual control. Thank you very much for accepting the invitation and presenting today, Andrea. And the floor is yours. Thank you.
Yeah, thank you very much for inviting me to this seminar series. It's really a pleasure to share this work. In particular, today I will talk about bridging the gap of reinforcement learning for meaningful games and meaningful control problems. And this is a work that was done during my PhD with my supervisor, Jean-Pierre Fouque, at the University of California, Santa Barbara, and in collaboration with Mathieu. So in particular, I will start with a brief introduction of some basic ideas from reinforcement learning and mean field theory, and then I will go into the core of the talk. So the goal, so reinforcement learning, first of all, is a branch of machine learning that is trying to solve a Markov decision process. And a Markov decision process is the framework where there is an agent that is interacting iteratively with an environment, and at each time, given his state xtn, he picks an action at tn, and the environment answers with a new state and a cost. The goal for the agent is to find the optimal strategy that minimizes the expected aggregated discounted cost, or in the case of the reward, like in case the cost is replaced by a reward, it would be like the maximization of the expected aggregated discounted reward. So in one of the most popular algorithms that has been used for years now to solve a Markov decision process in the case of finite state and action spaces is called Q-learning, and is based on the action value function Q star that is defined as the minimal cost that will be incurred by the agent if given the initial state equal to x and initial action equal to a, it will optimize starting from time 1 up to infinity. Is his own policy. Now, this function can be easily be reconnected to the classical value function of optimal control theory by applying an inf operator. But what is more interesting is that we can extrapolate the policy, the optimal policy, by applying an arg-inf operator. And this algorithm, as we will see later in the talk, is based on a learning procedure that is derived from the Bellman equation of the optimal action value function. In particular, since the environment is unknown to the agent, to the algorithm, it deploys like an epsilon greedy policy to explore and at the same time exploit the information that is currently available. The epsilon greedy policy, it works such that at each time, given a state x, it will pick with probability y minus epsilon the optimal action given the current estimate of q star, that is q tilde, or otherwise with probability epsilon, it will pick a random action across the admissible ones in the set A. So on the other hand, for mean field theory, the main core idea is the mean field interaction, which allows to describe complex models with among n agents. And this idea was initially used in physics to describe system of particles, but later on has been applied also in game theory. And in particular, we can describe an n-player game with the mean field interaction by introducing the empirical distribution of the states of the agents, both in the dynamics of each single agent and in its own cost. Now the goal in this case will be to find a Nash equilibrium that is a strategy alpha star such that any agent has not incentive to deviate from. And in particular, this is given by the relationship where the cost for the agent I, J alpha, Ji in alpha star is less equal than the cost incurred if all the players follow the strategy alpha star, and player I try to change his own strategy. Now, even though like the mean field interaction allows to simplify the analysis of these games, when the number of players becomes large, the cost of dimensionality comes back. And in order to tackle this problem, in the last 10-15 years, there's been like a lot of work in what is called mean field theory. Essentially, the idea is that we can pass to the limit n of the number of agents to infinity, and we can replace the system of an agent with a representative agent that is playing against the distribution of a population. I will give more details later on in the talk, but definitely you are all familiar about this. So a little review of the literature in terms of applying reinforcement learning to mean field problems. In the last years, there has been a little bit of a lot of work actually on applying reinforcement learning to solve both mean field game or mean field control problem, and usually this approach has been always be differentiated. And in particular, there's been a lot of work in terms of Q-learning, of extension of the Q-learning algorithm to mean field problems, but also in terms of algorithms that are based on what are called the policy graded algorithms. So today, what I will talk is the work that we did in this field that is relative, that in particular is relative to a unified approach that is based on Q-learning, that is based on the tuning of the algorithm. We are able to solve both mean field games and mean field control problems. Now, we started by applying this method to infinite horizon problems. And then later on, we extended to finite horizon problems with the interaction that was through the joint distribution of the states and the actions, so extending mean field problems. And we have also some example from finance. Then also we are working on extension of this approach to solve a problem in continuous spaces through a deep reinforcement learning algorithm. And we also introduce the same Q-learning algorithm to solve what we call the mixed mean field control games, which is like a competition across groups of cooperative agents. So I will start by speaking about the first work that is on the Q-learning algorithm for infinite horizon problems with the finite state and action spaces. And the first step that we had to do to approach this problem was to introduce new definitions of mean field game and mean field control problems. In particular, we introduced the asymptotic formulations in which the goal for the mean field game is to find a pair alpha at mu at, such that alpha at is the minimizer of the cost for the representative agent based on the distribution of the population of mu at, and mu at itself is the ergodic distribution of the representative agent given the pair alpha at and mu at. So what is important here, that the control function that we're going to find is not going to depend on time, since both the dynamics and running costs depend only on the ergodic distribution of the agent. And this allows to create like a framework that is similar to the reinforcement learning traditional framework, classical framework. Also, intuitively, this is the case where a single agent wants to join a crowd that is already at equilibrium, and the Nash equilibrium is represented by a strategy from which the agent of the population from which the agent will not have any incentive to deviate from. The same idea has been applied for mean field control. In particular, now we have a control problem of the making blast of type, where the distribution that is involved in the cost function and dynamics is the ergodic distribution of the population given the control alpha on which we want to optimize. So differently from the main field game, here we are not freezing anymore the distribution, but we allow the distribution to change depending on the control that we are trying to optimize on. So again, here the control that solve this problem, the solution of this problem is not depending on time, and this can be interpreted as the case of a central planner that wants to find an equilibrium, a strategy, such that there is the cost to add a new agent will be minimal for the population. So even though like this problem, both the main field game and the main field control asymptotic formulation are defined based on initial distribution mu0, the role of the distribution in there is no role of the distribution in the solution of these problems. So and also in the paper we show how this solution can be connecting to the solution of the finite horizon problem and to the solution of a stationary problem. So another thing that we had to do was to introduce the making class of Markov decision process, in which we have again the interaction of an agent with an environment, but differently from before, the environment not only generated the new states and the cost, but also update this estimation of the distribution mu n. So I want to give like an observation about this. Like here, what we are trying to do is really solving the problem with n-player games with a large population of players by only observing a single agent. So the environment itself in the algorithm later on will update the distribution based on the states of the agent by leveraging the symmetry of the problem. So the next step was to change the definition of the Q function, and for the main field game, this was pretty straightforward. Essentially, once that you fix the distribution mu, you have a Q function that is parameterized on mu, and simply is the cost that will be derived by considering mu in initial cost, in the cost for initial action and state action, and the cost after time one. And the Bellman equation is derived essentially the same way as the classical formulation for Q-learning. The situation is a little bit different for the main field control problem, where like these results does not apply directly. And we had to reformulate all the steps that are used in classical reinforcement learning to derive the Bellman equation. In particular, there is the main result that is the policy improvement theorem that is crucial for the Q-learning algorithm, that for the main field control case is a special derivation. And you can see the details in the paper. But what is the main change is that the distribution involved in this expectation depends like change between the initial time and all the times after one. In particular, for time from time one on, we have the distribution mu alpha that was also in the definition of the problem, that is the limiting distribution of the agent given the strategy alpha. But for the first time point, what is happening is that we have to consider like the distribution given the modification of this of the control function alpha based on the pair x con a. In particular, this new control function alpha tilde is such that for each x different from x, the control will be always alpha x prime, while for the pair x, in particular for the state x, the control will be given by a. So we were able to derive the Bellman equation for this new definition. And in particular, what is interesting is that we can find back like the quantity delta mu f and delta mu p that are in the continuous framework, that comes also in the continuous framework. Now, our algorithm is based on two updates rule. One for the distribution mu and one for the matrix Q. And the update rules are are defined on two learning rates, rho mu and rho q, and two operator, p calligraphic and t calligraphic. In particular, p calligraphic is when is equal to 0 will give like a stationary distribution for will be such that the distribution mu is stationary, so the distribution at the next time point will be equal to the same distribution at the time before. And the operator t calligraphing, when is equal to 0, is actually solving the Bellman equation that we discussed previously. So the role of the rho mu and rho q is essential in this approach. Indeed, if we have a ratio rho mu over rho q that goes to 0 as k goes to infinity, the update rules tracks the ODE system that is shown in the slides, where epsilon is sensitively lower than 1. And here we assume that equation 2b is a globally asymptotically stable equilibrium for each fixed mu, so that if we consider a Poisson distribution for the population, we can find like an equilibrium q mu from which we can derive the optimal strategy. And also the equation 2a as a gas equilibrium, so that we can find mu infinity, so that pq infinity, mu infinity is equal to 0. And this actually implies that the pair mu infinity and corresponding control function derived for q mu infinity forms a Nash equilibrium. Now the situation change if we reverse the ratio and we consider rho q to rho mu going to 0 as k goes to infinity. Well, now the system is different from the one that we had before. In particular, what we are assuming here is that for each fixed q, we have a solution of the first equation, which means that mu q is the asymptotic distribution of the population that is behaving following the control function derived by q. And also the second equation is a gas equilibrium such that q infinity, such that the operator is equal to 0 in the pair q infinity mu tilde q infinity, which means that q infinity satisfies the mean field control Bellman equation that we introduced before. So we designed this algorithm that is for problems with the finite state and action spaces, and which tries to take care of the trade-off between exploration and exploitation using an epsilon greedy policy. So we initialize the Q matrix equal to 0 for all entries x con a, and we start with initial guess of the limiting distribution as a uniform distribution over the state space. Now we iterate different learning episodes, and at each of these episodes, we run paths that are between 0 and capital T, where T is large, and we have two update rules. One that is for the distribution of the population, that is based on the current observed state x con n k, and there is an update rules also for the Q function, which is derived based on the contribution that is from the Bellman equation that we saw in the previous slides. So the main role in this algorithm is by the two learning rates, rho mu and rho q, and we will show in a minute how the difference between them gives like different results in the solution. Now, the stopping rule for this algorithm is based on the difference in the estimates between two different episodes, learning episodes, for the distribution mu and matrix Q. So here I show like the learning schedule that we can use, for example, to solve a mean field game or mean field control problems. On the left, we have in blue, the learning rates for the distribution mu, which is lower than the learning rates for Q. And this was is actually mimicking the solution of the main field game, where we want to freeze the distribution mu, and then we want to obtain the optimal strategy. While on the right, we have the different situation when actually the rates for Q are lower than the rate for mu. And this is because the distribution for the population needs to change accordingly to the change of the control function that is derived for Q. So here I will introduce like an example of the linear quadratic family that we tackle with this algorithm. In particular, we consider an interaction through the first moment of the population of the population, and the drift limited to the control of the single agent. So the running cost is defined based on different terms. So the first term is the cost for choosing the drift. The second term is an incentive to be close to the quantity C2M. And you can think that if C2 is equal to 1, then it's actually the mean reverting property. Then the third term is an incentive to be close to a target C4, and the last term is in order to be different for the population to be far from 0. And in particular, this term is important because otherwise the solution of the main field game and field control problem will be the same. So it helps us to differentiate the two problems. So here I show like the results by running the algorithm in with two different settings. In particular, on the left, we tune the algorithm to solve the main field game. On the right, we tune the algorithm to solve the main field control problem. And each of these plots is representing on the x-axis the state of the agents. On the left y-axis, we have the control function alpha x, and the right y-axis, we have the distribution of the population. In particular, the red line is the continuous function that is solving the mean field game. And the blue line, we have, is a continuous function for the control of the mean field game. The blue line is the control function for the control of the mean field. I'm inverting. The red is mean field control and the blue is mean field game, and the green lights is actually the distribution of the population. And even if like these two plots, they look similar, I want to point out that the center of distribution is different. For the mean field game, we have the mean to be in 0.8, while for the mean field control, the mean is actually 0.05. Now, the black dots are the control learned by the algorithm, and the dashed line is actually the distribution estimated by the algorithm. So you can see that the learn solution depending on the tuning of the parameter, change towards the solution of the mean field game or the solution of the mean field control. And also, I want to explain the behavior on the tails of the distribution. So these algorithms are based on the exploration of the environment. So as long as you have exploration, you can obtain a better accuracy of the solution. But where there is no exploration, the algorithm will be not able to learn. And since like the distribution is concentrating in the center, like we will see a better solution in terms of control for this area, while on the tail of distribution, where there is a lower exploration, the distribution will be far from the theoretical solution. So here I will explain an extension of this approach to finite horizon problems with the interaction that is through the joint distribution of the states and the action. So we consider the classical problems. So here we have the pair alpha at and nu at, where nu at is the joint distribution, and is appearing both in the running cost and the dynamics, and as well, and its marginal distribution is appearing in the terminal cost. So we have to solve a fixed point for each point in time between 0 and capital T minus 1. And in this case, the control will be depending on time, differently from before. the same can be obtained for the mean field control problem. We have always an optimal stochastic control problem of the making class of type, and the distribution involves the joint distribution, and this is like, they are also called extended mean field games. Now, the algorithm is more complex than the one before, because like we are not dealing anymore with a unique Q function, but actually we have a Q function for each time point. So we have a three-dimensional matrix to estimate, and we also have a distribution that has an estimate for distribution for each time point of the discrete, for each point of the time discretization. So the updates rule are two as before. We have one for the population distribution of the population that is similar to the one from the previous algorithm, but what really changes the one for the Q matrix, because here the matrix at time n is updated based on the knowledge of the matrix at time n+1, which increase the complexity of the algorithm with respect to the previous version. We apply this algorithm to two problems arising from finance. One is the mean field capital accumulation problem that was discussed in Wang 2013. And in this case, the process X alpha theta is modeling the wealth of the agent involved in the production of a good. And its dynamics are driven by a capital function, a capital G function that is relative to the production function, which is based on the mean behavior, the population behavior, investment behavior, plus a source of noise WT, and alpha T is the investment level of the single agent. So the goal for the agent will be to maximize the estimated aggregated discounted utility function of the consumption, where the consumption is the difference between the wealth and investment level. So all the money that are not spent in investment will be consumed from the agent. And the utility function chosen is an hyperbolic absolute risk aversion utility function, which depends on a parameter gamma that is between 0 and 1. So this is an extended mean field game, is a finite horizon, and also is not of the linear quadratic family as a multiplicative source of noise. So essentially we are in a family that is different from the classical linear quadratic, and this shows that the algorithm is pretty robust and is not, it doesn't leverage any property of the linear quadratic case. So here we have the convergence for the control functions learned by the algorithm. On the top, we have the case of mean field game. On the bottom, we have the case of the mean field control. We have three plots because we are considering three different time points. And the blue triangles are the solution of the mean field game, the theoretical solution of the mean field game. The green square are a numerical approximation of the solution of the mean field control problem that we obtain through a deep learning solver. And the red stars are actually the solution obtained from the algorithm. So as before, you can see the same behavior as before. We have that based on the tuning of the parameter of the algorithm, we can converge to two different solutions. And also in the area where there is no exploration, we have no learning. And this is consistent with what we were observing before. Also, here I'm showing like the evolution of the estimates of the first moment of the law of the actions and through different learning episodes. Each plot is relative to a different time point. We have always on the top the mean field game solution, on the bottom the mean field control solution, and we have on the x-axis the episodes, and on the y-axis we have the estimate of the first moment of the law of the actions. So you can see on blue line, the blue line is the solution of the mean field game, the green line is the solution of the mean field control, and we can see how the algorithm is converging to the solution at each time point. So just a comment on the last time, we can see that there is quite a gap between the theoretical solution and approximated one. And this is due to the fact that we are using an epsilon greedy approach. So even at the last time points, at the last learning episodes, there is always probability that the algorithm will try actions that are different from the optimal one, and this exploration explains like the gap between the theoretical solution and the approximated one. In particular, this is more evident for the case where the solution is zero. It's zero. That is the case of the last time point. So the second example we analyzed was a mean field execution problem, where the process xt is modeling the number of shares of the representative trader. And in particular, in this problem, the goal of the traders is to liquidate their position by a final time, capital T. So we have the cost function for each trader that depends on the control alpha and also on law of the actions theta. And in particular, we have in the running cost, the cost for the choice of the drift, a penalization of the current inventory of the trader, and also a factor that is due to the aggregated price impact, and which depends on the distribution of the action of the crowd. And finally, there is a penalization for the inventory and final time, capital T. So I just forgot to mention that this was introduced by Carmona and Lacker, I think in 2015, and is also discussed in the book from Carmona and Dalariu in 2018. Here we have the convergence for the control functions. In particular, as before, we have on the top mean field game and on the bottom mean field control. We are plotting different time point from left to right, and on each plot we have the state on the x-axis and the action on the y-axis. We have the blue line that is the solution for the mean field game, and the red line that is the solution of the mean field control. So for this case, we have a good approximation of the solution of the mean field game for each time point, while for the mean field control, the solution is good at the beginning, but it degenerates towards the end of the interval. And we have to, there is like a comment that I forgot to give you before, is that we are applying algorithms that are designed for finite horizon problems to continuous to problems in continuous state and action spaces. So there are some errors that are due to the truncation of these spaces, to the discretization of these spaces, and also the discretization of time. And this apparently seems very impacting particularly the solution of the mean field control problem in this case. So we are working on an extension that is applying other techniques from deep reinforcement learning to solve problems in continuous spaces, and we are planning to come back on this problem later on with better results. Here we have the convergence for the estimation of the first moment of the law of the actions, and again, mean field gain on top and mean field control on the bottom, different time point from left to right. And in particular, we have on the x-axis the episodes, the learning epsilon k, and on the y-axis we have the estimate of the first moment at episode k. So you can see the blue line is the value of the solution of the theoretical solution of the mean field game, and the red line is the value of the solution of the mean field control problem, which is changing across time. So you can see that at the beginning the solution is around -1, then it goes around 0, and then finally reach value 0. For the MFG game, we have an approximation that is learned very quickly and with a good error, while for the MFG control, the approximation is good for initial time point, but degenerates towards the end, as we saw for the control function. Now I will give, like, if I have still some time, I will give like some ideas from the work that is in progress. In particular, this is applying deep reinforcement learning to solve these problems in the case of continuous spaces. And they are based on what is called the actor-critic approach, in which we have two entities: the actor that is that refers to the policy, and the critic that is referring to the value function. And at each step of a learning episodes, the agent, based on the state X, choose an action given the actor. And this action will trigger new states and a cost that are used for evaluating the value function and to define the temporal difference error, that delta Tn, that is used to both update the estimates of the value function and the policy itself. So in order to explore the algorithm, the environment, in this case, we don't have an epsilon greedy policy, but we have a Gaussian policy, pi, that is that has mean, mu, and sigma square. And the idea is that once that the algorithm converges to the solution, we expect the sigma square to degenerate to 0 to obtain a deterministic control function. The critic is the value function from which we can define the temporal difference error that is similar to the quantity that we were using for the updates of the Q-learning, and is actually derived from the Bellman equation in a similar way. So the algorithm is designed for now for a problem where the interaction is through the first moment of the population, of the population, and for finite horizon problems. So we have 3 learning rates schedules. So this is why we call it as a unified 3-scale mean field actor critic algorithm. And we use 2 neural networks for approximate the value function and the policy. And we use a scalar estimates for the first moment of the law of the states. Then we iterate different learning episodes, and at each each step of the learning episodes, we have 3 updates. One that is involving the critic, that is based on a stochastic gradient descent approach. The same is done for the actor. And finally, we have the same update rule that we use in the Q-learning approach for updating the mean field term. So the stopping rule is based on the value of the gradients and the updates on the estimate of the distribution. So we have some results for applying these to the linear quadratic problem and the mean field capital accumulation problem. And in particular, what is important is always to choose the schedule of the learning rates. And we have that already Borkar in 1997 discussed the actor critic algorithm as a 2-scale stochastic approximation procedure. In particular, we have that the learning rates for the policy pi should be lower than the learning rates for the critic. And this is because what we want to do is essentially something that somehow it reminds me the mean field game problem. You want to freeze the policy in order to evaluate the corresponding value function. And since we are using 2 neural networks, we applied Adams stochastic gradient descent approach with this choice of learning rates. And for the mean field interaction, the learning rates that is used depends on the choice of the problem. In particular, we want for the mean field game values that are very small compared to the one that we choose for the mean field control problem. because we want to replicate the freezing of the distribution or the quick update that we have in the mean-field control game, the mean-field control problem. So here we have the convergence of the algorithm in two different settings. In particular, if we choose the parameter omega to be 0.7, where omega is essentially the power of using the learning in the definition of learning rate schedule, then we have the algorithm to converge to the solution of the mean-field game. Here you can see that different from before, the solution obtained by the algorithm is a continuous function due to the nature of the neural network. It's not anymore, it doesn't not requires anymore a discretization of the space or a truncation of the space. And also we are able to learn on a domain that is bigger than the one that we were analyzing before. So it's more powerful in terms of extending also in the solution also in area where the exploration is low. In particular, on the left, I'm representing the control. We have the state on the x-axis and the action on the y-axis. While on the right, in the plot on the right, we have the estimates of the first moment of the states. And in particular, we have the blue line that is the solution of the mean-field game. Sorry, here I confused the color. It's the mean-field control of the blue line, and the red is the mean-field game. And black lines is how the estimates obtained from the algorithm evolves across learning episodes. And we can see that for the mean-field game, there is like a convergence that arrives very quickly and is also stable, while for the mean-field control, the behavior is more noisy. And this is due to the fact that once we use omega to be so low, we have the distribution will change very quickly in order to follow the change in the policy as is done in the mean-field control framework, and this generates a behavior that is more noisy. And this actually is something that we are still trying to solve, because we have like a stability in the solution of the mean-field control, and this is still in progress. Another application of this problem was for the mean-field of this algorithm was for the mean-field game framework of the mean-field accumulation problem proposed by Wang. In his paper, in particular, there is also the solution of the infinite horizon problem. And we take the same example discussed in the paper, and we were able to reproduce to approximate the solution both in terms of the control function and in terms of the first moment of the limiting distribution of the action, of the law of the action. So this is also interesting that if you look back to that paper, is also approaching a new definition of mean-field game in infinite horizon that recalls a little bit the definition we propose for asymptotic mean-field games. So in terms of the control, we have a very good approximation of the control function from our algorithm, and also in terms of the first moment of the distribution, we have an approximation that is converging to the solution and is pretty stable. So now I will conclude by summarizing what we discussed. We presented two new definitions of asymptotic mean-field game and mean-field control problems with the infinite horizon. We adapt the Q-learning algorithm by introducing a new definition of the Q function, both for the mean-field game and the mean-field control problem, and in particular, the one of the mean-field control problem required to prove a new Bellman equation. And we propose a unified to-scale Q-learning approach to solve mean-field problems in finite spaces and with the finite and infinite time horizon. And we also propose a 3-scale deep learning reinforcement learning approach to solve the infinite horizon problem in continuous spaces. We have some example in terms of linear quadratic family, and also outside of this family with application in finance. And what we are working on is an extension of the deep learning approach to more general mean field problems that involves not only the first moment of the distribution, and also involves the joint distribution of the state and action, and hopefully also the finite horizon case. We are working on the theoretical analysis of this 3 time scale approach, and in particular, there is like an issue coming from the fact that we are applying neural networks, because then the rates are different for the estimate of the population and estimates of the actor and the critic. And this is something that we are also trying to study. And we also want to apply then this algorithm to solve other problems in finance, like the trader problem, in particular for the mean field control case, where we were not able to obtain a good approximation with the Q-learning approach. And also there are other problems in finance that has been treated with mean field theory, like the systemic risk problem that we were planning to work on. So thank you very much for your attention, and let me know if you have any question and you want to discuss it more. I will be super happy.
Thank you very much, Andrea. It was a very nice talk. Are there some questions or comments from the audience? Feel free to unmute yourself if you want to ask questions, or you can ask in the chat if you prefer. Okay, I have one small question about the learning rate in the 3-scale approach. So you use the same learning rates for mean field gain and mean field control for the top part. So for the actor and the critic, you use the same learning rate. Okay, and so the only thing that changes is the rate for the distribution. Yes, correct. So for now, we are using both the same learning rates for the 2 networks, and we change the learning rates of the mean field term, but we are testing different approaches. So I tried a stochastic gradient descent approach, where you have a learning rate schedule that is actually dynamic across learning episodes, and I also tried this Adam stochastic gradient descent optimizer, where the learning rates are fixed, but is actually is not, they are not really fixed. You choose a parameter, but then internally the optimizer is varying the learning rates depending on the values that that it occurs on. So, but again, the mean field control is not stable yet. It's not very robust, the solution. So we are trying to improve that, and I think there is there's going to be some work. And I'm not sure if we're going to keep like the same strategy. I think that it will be important to find a way to make these learning rates comparable, and so like having a relationship with across the 3 learning rates. I think that will be more the strategy that we are going towards now. I see. Okay, thank you. You're welcome. Other questions or comments?
Hi, I had a question.
Yeah, please.
Hi, Andrea. Very nice talk. I really like the work. I had one question about the 3 time scale algorithm. So am I correct in believing this? So do you use the agent's dynamics itself to update the mean field, right? So there is no like a mean field oracle. Right. Yes, we use like the states observed by the environment. So we don't have, the algorithm does not have direct access to the dynamics, but we observe that states that are sampled, and based on these states, there is like the updates of the learning
of the estimate of the mean field. In particular, here we have only the estimates of the first moment, so it's not even
okay.
It's not
Okay.
even involving the full distribution for now.
Okay. Okay. Yeah, that's very, very interesting. Yeah. Thank you for the talk. It's very clear.
Thank you.
Okay, thank you. More questions or comments?
I have a question, maybe
Yes,
more a
please.
curiosity. And I would like to ask which kind of software do you use for the numerical simulation, and if the curse of dimensionality was really an issue also concerning the simulations. Thank you.
Thank you for your question. So I'm using, in particular, well, for the Q-learning approach, simply Python and with the classical libraries. For the deep learning approach, I'm using some PyTorch, so and TensorFlow within Python. And in terms of the Q-learning, the problem is really the complexity of the problem can really be controlled by truncating the space and discretize the space in a way that you don't the complexity doesn't raise too much. In particular, Q-learning is very sensitive to the dimensionality of the Q matrix. So if you use too many states to find discretization, then the algorithm is not going to converge. But in terms of time, it's not very intense. I was running everything on a server because I was parallelizing through different runs in order to have average over different runs as a solution. In terms of the deep learning approach, for now I'm using fixed number of learning episodes, but however I have in particular different for the mean control case. There are some issues of stability that I was mentioning, and this brings the algorithm to reach some not unnumbered regions, so it diverges. Essentially, there is an explosion of the gradients. So what I'm trying to do now is to define a different approach where rather than applying a fixed number of learning episodes, I have like some stopping rules, like early stoppings for TensorFlow, where essentially based on the values of the gradients, the algorithm is going to stop automatically, and this will also allows to reduce the running time. But everything is something that you can run on your laptop. It doesn't require any special hardware.
Okay, thank you. And just to there is something that you put on GitHub or something like that too about the code of this.
Not yet. We, especially the deep learning, is still a work in progress. So maybe we will think about like a repository later on when we have like a submission.
And then last question, if you was thinking about putting also some uncertainty into account, I don't know.
Which kind of uncertainty are you speaking about?
Maybe regarding the dynamics of the
dynamics are stochastic already. It's like it's always there is always a source of noise in all the examples, so it's not the problem is not deterministic, and also there is always an exploration of that is obtained through some stochasticity, both in the Q-learning and in the deep learning approach. In particular, here the policy is probabilistic. Is a normal distribution at the beginning, and once the algorithm is converging, the variance goes to 0, and then it becomes deterministic.
So you obtain also a confidence interval at the end of the
Okay, yeah, we have some. We haven't done that analysis, but yes, we have also the confidence interval, because we can run, different. Each run is going to give like a different solution, because the algorithms are stochastic, and then you can have like the average, the confidence interval, and everything.
Okay, thank you, and very nice.
Thank you.
Thank you for the question and the answer. Andrea, there is also a question in the chat about what is the number of agents in the simulation, used in the simulation.
Yes, correct.
So,
I think
yeah.
someone already answered. Yeah, you already answered. So
please feel free to.
Yes, give me a second. I'm reading. So the idea is that when in the formulation in a mathematical framework of these problems, the main idea of mean-field games is that you pass the number of agents to the limit, so you consider n goes to infinity, and then the problem is replaced by the problem of a single agent playing against a law that is representing the distribution of the population. Now at the equilibrium, what is happening is that the solution, the law of the single agent is actually matching the law of the population, and this is due to the fact that the game is symmetric. So each you cannot differentiate across players. So we use this idea in order to define some approach, some algorithms that are actually analyzing only the single agent, because the states of the agents, they will be at equilibrium sampled by the same limit, the same distribution of the population. So we leverage that idea in order to avoid the simulation of n agents, and and also what we did was like in learning, you have like there is like this idea that you can sample for a distribution that is different from the extra distribution, and you correct your estimate step by step. So we apply the same idea where we consider, okay, we start with an initial guess for and that is the distribution of the population, and then by learning we will converge through this distribution of at equilibrium. So it's more or less the same framework. I hope this answered the question.
Right, that's the same continuation, but in practice, say you think you want to apply this approach to the system with 5 agents, is it, or 10 or 100 agents?
Okay.
It would work. When this practical behavior would approximate the mean field ideal theoretical prediction.
Yes. Yeah, essentially there is if you look at the book from Carmona and Delarue, that you can also find a better answer than the one I'm going to provide now from them. Is essentially there is the definition of what is called the master equation that connects the solution of the n-player game to the solution of the mean-field games. So essentially, the mean-field games is shown to be an approximation of the solution of the n-player game, and I think the error should be of the order 1 over n, or 1 over square n. I don't remember exactly, but there are some approximation results between that connects these two problems.
Yeah. Okay, thank you.
You're welcome.
Thank you. I think there is another question by Thanos. If you want to ask a question.
Yes, thank you for the presentation. Sorry for my voice. I am sick.
No worries.
If you don't hear me properly, tell me and I can try to write on the chat. In fact, I have several questions. The first is, what is the, if you imagine that behind we have a continuous time problem that you approximate by this discrete time problem. Do you see the influence of the time discretization? Can you see it from your approach?
Yeah, this is a very good question. Indeed, there is an influence of the discretization because essentially you have always, when you discretize, you have always to connect the discretization in time to the discretization of the space, and the discretization of the space has an influence on the stability of the Q function in particular. So then you have to, it's like a back, back process, in the sense that you start by backward process. You start by picking like a distribution of the states, which allows the convergence of the Q function, and based on this discretization, you define a discretization of the time interval. And there are some results about the connection, the influence of the discretization of the space on the Q function, and I don't remember exactly the reference, but if you want, I can send you. And is also mentioned in the paper from Gu et al., in which they recall these results. And yes, let me know if you want more reference. I can provide them.
In fact, I wanted to ask about you, like if you see this, or if you could do the calculation to compare what you get from the algorithm to the kind of theoretical solution, in some sense. If you could compare the law that you get from your algorithm to the theoretical solution. So you could see some influence in the error from the discretization.
Yeah, we don't have like an analysis of the error of the algorithm. For now, like we have like an analysis of the convergence results for the two-scale approach, and in terms of the quality of the approximation, is like it's more empirical for now. You can see from the plots, like let me go back.
Yes, like I saw the plots, and this is why it came to my mind. If you had any results, or if you could quantify more the estimates. This is how I got to the question.
Yes, that's a good question. We haven't done it yet, but definitely something interesting to do. I can give you like an insight. The mean field control problem is always more noisy. In particular, here we are not only averaging over 10 runs, but we are also averaging over the last 10,000 learning episodes. And in particular, the last average is something that you need for the mean field control problem, because the point is that when you allows the learning rates to be so small, and to allow, to be so large, and to allow a very quick change of the distribution of the agents, of the estimates of distribution of the agents, then you have a behavior that is very noisy. And this is particularly true for the mean field control problem. And we fix this by averaging over the last 10,000 episodes. But so it's, yeah. So I think it's definitely interesting to proceed to an estimation of the error, but it's something that we haven't tackled yet.
Maybe if I can add something also in this plot, it's for the stationary case. So in this case, maybe the time discretization does not play a big role, but if we take a non-stationary problem, maybe finite horizon, then the time discretization would maybe play a bigger role. What I'm not sure is if there is a big role played by the algorithm on top of the, I don't know, Euler-Maruyama scheme, for example. I mean, there is there is an error of discretization that we can analyze through the discretization of the SDE. But
yes,
maybe on top of that, there is an error of the algorithm. This, I think, we have not, we have not investigated.
Yes, it's a very good point. Yeah, there are. Yeah, definitely. Thank you, Mathieu, for giving more insight.
One more, if I may ask one more question. Maybe it is a stupid question, but you mentioned that for the omega in the linear quadratic case, that then the MFG and the MFC will be the same. And also in the case of a potential game, like a game with a potential, they are going to be the same. But the algorithm is going to run the same. Like, what is going to give you the algorithm if you have the same
solution? Yeah. So that's actually, that was something that we, found at the beginning, because we started with the initial running cost that was not including the last term, and then we were ending up with the same solution for MFG and MFG control problem. And an algorithm, well, it converges to the same solution. Simply, we have a solution that is more noisy for the MFG control because the parameters are chosen such that the behavior is more, the distribution is more jumpy.
Yeah, it was that simple. I mean, I had just the curiosity. It was maybe a stupid question, but
no, it's
thank you.
You're a nice question. Thank you for asking. It's always nice to have a discussion.
Okay, nice. Thank you very much. I don't know if there are other questions. Okay. Well, otherwise, thank you very much, Andrea, again, for the very nice talk. Thank you, everyone, for attending.
Thanks a lot for inviting. It was very nice.